Hey, Shaman.
Oh, hi, Sajwa.
Hey. Oh, thanks a lot for coming.
Oh, Gary, you look so dark.
Okay, 1 second. I'll turn on the light.
Hey.
Hi.
Okay. So, yeah, I'm gonna actually try to explain. Maybe I try to quickly explain how to get the sparse cut again, because I feel it was a bit confusing, and I think there is a way to make it less confusing. And then we will go into how to use dynamic tree to speed things up. Yeah. And you see my screen, right? Okay, good. Okay, so, and so what I hope to, so in class we have seen how to use how to compute, like how the push relabel algorithm take only like this much time, and like it basically transform a valid state to valid solution. Okay, in this time. And now in the MaxFlow setting, when we set the h to be n+1, I hope that this is a case which is not too confusing in class. This is fine, right, in class? Yeah. Okay. Like, but the idea is that like when there are a lot of like when h is big enough, then at the end after the algorithm, we know that there is some level which is just empty, and then if we just look at the cut of level of our vertices that contains our vertices of level more than k, then basically we have this thing that the number of like all flow that goes out of this are saturated. And actually, basically, when you find a cut, when you want to compute a max flow and min cut, and if you find a cut such that the flow that go out of that cut is saturated, is fully saturated, it really just implies that your flow and your cut like is optimal because this is just tight. Okay, so now let's look quickly into a sparse cut or matching embedding again. And the problem was defined in class. We have a graph, we have set A and B, and we either want to find sparse cut or we want embed a matching like B matching, where each node here have degree, like the matching that we embed, each node here send degree unit of flow, and each node here receive at most degree unit of flow. Okay, so if we want to embed such a thing, then with like this M with this congestion, then it's kind of clear what we actually like just from the goal that we want to embed M and with this congestion, it's clear how should we define the graph and the source function and the sink function. Why? Because we really just define the source function to be such that each node from A want to send this much flow. Each node in B can receive this much flow. And every edge in the graph, we define GC to be such that the edge have this much capacity. So we really just define this as our input. And if we can manage to find feasible flow with this input, you see, right, that we really just embed M into the graph. The flow, the feasible flow is the embedding of M with this properties. Yeah. So from our goal, it's already like it kind of dictate us what kind of flow problem we should define. We should define a sink and source function like we define it here, and the capacity here is just dictated by the congestion here. All right. And now, as a warm up, actually, let's try to say that we will use this as our input and call the basic push relabel algorithm. But let's say that we set h to be n+1 still, right? And see what happened. So if when we run the algorithm and at the end, after termination, there is no excess, then as I just described, as I just explained, the flow that we got is a feasible flow that satisfies this source and sink function, and this flow would correspond to n. So we are done in this case. Now let's look at the case when the excess is more than 0. Okay, when the excess is more than 0, but when we choose h to be as big as n+1, we would still be able to get a cut such that the flow out of S is saturated. Like just use the same algorithm, will be you get a cut S such that like this level is empty and everything that go out, the edge that go out is skipping level and they are saturated. So F out is this. Just from the same case from in the max flow case. And let's see that I claim that this cut will be a sparse cut. And the reason is here. So first, what do we have? When we say that the flow that go out of S is saturated, it is actually, I should say it's saturated in GC, right? Because this is a graph that we work on. So the total flow out of S is this much, because this is the cut size in GC, but GC, every edge in GC have this capacity. So on one hand, we have this much. On the other hand, we have that the total flow out can be written in this way. Just because you have that the initial mass is basically either go out of S or remain in S, or like absorb in S, or like remain in S as an excess. So that's why we have this one. And the absorbed of S is just total sink in S, and this is more than 0. Okay. So what we have here is just
Is it
that.
S or X?
Yeah, it's S here. Thanks. Yeah. Right. So what we have here is like, it basically says what? It says that this is a cut such that like even if you allow each edge here, like even if you allow every edge here to have congestion 1/5, the total flow, like what we have here is that the cut size here, even if you scale the cut size up by 1/5, this thing is still less than this. Okay. But this thing actually will be less than the volume of the cut. And this is the reason, like, and why is that? This is just like from the class, right? Because if this is A, this is B, and if this is S, A, then you can see that like the source that we want to send out, this total source in S is less than the volume. Yeah. So think like this, like here we have a cut, and the total source that we want to send out of a cut is just at most the volume of a cut. Like the total source is at most the volume. But you got stuck. Even when you say that each edge you allow this much congestion. So basically this thing is less than the volume, which is why the cut is sparse. Okay. So, and to be able to compare these two things together, we use like a F out as a way to bridge these two things, because we know that there is a cut such that the flow going out is saturated. Does it make sense? Okay. Yeah. So this thing is at most volume of S, and you can do, like, you can show that this is also less than volume of S bar. But I will let you try to do it yourself. So at the end, we can imply, like, just by here, these two things, this together, we get that the cut is sparse. But okay, it works, but it is slow because we set h to be n plus 1. Now, what I want to say is that like everything still like almost works as if it is the same, but it works even when h is small too. And the reason is here, like just call the same algorithm when you set h to be much smaller than n. And if it turns out that you can send all the flow anyway, there is no excess, then you're good. You're done. But if there is still excess, then we want to say that we get the same thing. We get like a 5 sparse cut, but maybe not quite 5 sparse cut, maybe 1.15 sparse cut. And from the previous case, we said that if h is very big, then we can find a cut such that the flow out of s is saturated. And this is saturated in GC. So it is this much. Here we will say that something similar happened. That is, okay, h is smaller, but know that we actually will be done too if we can find s such that the flow out of s is almost saturated. Not exactly this, but you allow this much slack, right? Because if you have this thing, then, well, just from this inequality, you have this minus mean of volume as volume S bar here, and this thing just move into other side, and you get that like instead of phi here, you get like some a bit more factor here. Make sense? Yeah. So like all we need to do is just to say that we want to cut such that, okay, a cut such that the flow is not saturated, like almost saturated along the cut edges, but except some small thing. But how small we can do? Like this much small. Yep. Right. And now, so how to find such a cut? Well, this is a place where we do like a look at for each level. We will say that there must exist a level such that this is true. Yeah. And so the claim formally is here, right? There must exist a level k such that flow out of this cut, like there is a prefix cut here, level at least k, such that flow out of this cut is basically almost saturated except something. And by scaling, you get this. Yeah. And now, well, it's kind of similar to what we did in class now.
What is K here?
K is just like some level. Like I'm claiming that there exists some K such that this is true. Yeah. Like before, when h is like n plus 1, K will be some K such that you don't have this term, right? But now you allow this much. Yeah. And how do we do this? Well, like, because you basically, like, let's look at this. Like we look at this G consecutive, like G con that contains all edges between the consecutive level, and now the argument will be the same as in class. That is, when you look at gcon, there must exist one level in gcon such that the edges, the cut edges in gcon here is sparse. Yeah. So we will have this, and if we try to use the claim, like this important claim from two sides, you actually have that this thing is less than this, but also the complement of it. So this thing is less than this, but also the complement of it. Just do the same argument from the two sides. And but this is
Maybe one quick question here.
Yes.
So when we do the argument from both sides, so if we use the argument twice, then the k could be different, right?
Yeah. So
we are actually using the argument like the ball is growing from both sides at the same time.
Right. So basically, when you grow a ball from both sides,
Okay.
like you get one cut here, and maybe you get another cut here, when you grow from other side. And if you take the smaller one, like if you take a small, like let's say this is the first cut, S1, this is second cut, S2, and which one has smaller volume, take that one. Then it will be like this thing will be true for both sides. Yeah. Make sense?
Yeah, I guess that's true. Right. Thanks.
Yes. Yeah. Like use the same argument from both sides and choose a smaller one.
Maybe 1 minute here.
Mm-hmm.
Because this is like so for these S1 and S2, they have respectively this kind of property, but so if S1 is smaller, then its cut size is could also be like a bit smaller, right? Because it only need to satisfy that the cut size is at most 5/20 times the volume.
One sec. So we should choose a smaller one, the one that has smaller cut size, I guess. Yeah, not the smaller volume. Right.
I see. Yeah. But then the volume could differ or not.
Let's see. I
was thinking about like growing the ball from both sides at the same time. Like at the beginning, we have both the first layer and the last layer, maybe.
I don't think that that is a good idea. Let's see.
Yeah, that's.
You don't have to choose the smaller cut, right? It's like as long as they satisfy this inequality, then that will be one valid cut.
Yeah. So actually, like maybe the claim is this. Like suppose that you just grow ball from this side, and if it turns out that this one has volume at most half, then then you're done. But if this thing has volume more than half, then if you grow from other side, you will be done. Yeah.
So it's impossible to have like both S1 and S2 larger than half?
Yeah, because like this is where we actually need that edge. Let's say that we grow ball up to this many layer, like up to this many layer, but let's say that this is like less than half of our, like we set edge to be more than maybe 100 or 1,000 in. So what I mean is like S1 is always like a half level or always strictly greater than H over 2, and S2 is like, so both cut are disjoint. Yeah, these two cut are disjoint.
Yeah, I believe there's a way to make this work. Yeah, I guess it could be verified more carefully.
Yeah, sure. So what I want to point out is just like maybe the good intuition to think about the problem of finding sparse cut is just still think about the case when H is big, and like look at this inequality that we have a cut such that it's saturated, like that the flow saturated cut, and by the way that we define the problem, you will get a sparse cut. But this argument basically just work even if we get set H to be as small as this thing, because we will still find a cut S such that the flow is almost saturated, and the argument just still work. Yeah. So so that is the argument for sparse cut. So I will just leave it at this, and now let's see how to make everything faster. Yeah. Okay. So if you recall, the algorithm for push relabel take this much time when the parameter, when you are given parameter h, and that give us like this running time of this application, and we will try to improve it to mh and log in. Yeah, and the strategy is here. So if you recall, the bottleneck was the number of saturating push, right? There are a lot of saturating push, like mh squared operation of unsaturating push. The saturating push is just mh, and the total cost of relabel is also small, like it's also mh. Do you recall why the total cost of relabel was mh?
Is it not NH?
Yeah, nh. I mean, it's nh, but we also do this charging scheme where the
Degree we attribute it to
Yeah.
the vertex, right? Okay.
each node, when you try to scan for the admissible edge at U, we spend degree time, and we charge this degree time to a relabel, and that's why the total cost of relabel with this charging scheme is going to be mh for but anyway, this is a bottleneck and we want to avoid it. Yeah. And the strategy is that somehow we will make all of the push to be saturated somehow. Yeah. And if we can do that, then this thing is gone and everything will be NH. And to implement this, we will use something called top tree. There are many names for this data structure, like dynamic tree, link cut tree, topological tree. Like they are like these have different name because they use different implementation. And but top tree is like an API that is very convenient, and you can implement it using this thing. But so I will just talk about top tree. It provides a most convenient API. And I will talk about top tree in a very high level way, like as a user, not how to implement it. So top tree data structure is the following. It is, imagine that you maintain a collection of rooted tree, like there are like a T1 here, T2 here, and so on. And each edge have some value, HE have some associate value E. Yeah. So morally speaking, top tree allow you to basically update and query anything in this collection of tree. Like when you want to maintain something dynamically in the collection of trees, you can do it. That's the rule of thumb. Yeah. So let me give you an example of what you can do. The first thing that you can do is, for example, you can cut edges. So let's say you cut this thing. So now this thing become a new tree, and this thing become this. Or you can add edges between the two trees. Like maybe you add this root to this, or yeah, or make this to be this. Make this root to be a child of this guy. So as long as your collection remains a set of rooted tree, that's allowed. Yeah. And so that's like a very simple, like it's like you add and delete edge as long as you have a collection of rooted trees. Now comes the more advanced kind of update. So let's say that you have this tree. And I say that I choose two nodes, U and V. Then I can say that I add the value of V. Let's call this path from U to V. So what this change path X, like X, Y, V do is that it just add the value along this path by V. So this is plus V, plus V, plus V, plus V. So like even if the path is super long, you can do this in one operation, and it's still very fast. Yeah. Okay. And there are many more things that you can do, but we will not need it. For the query, you can also like say that, okay, give for each node U, give me the root of a tree that contains this node. Or like, now this is an interesting one. Give like, I query X and Y. Maybe X is here, Y is here. And it will return, like, it will look into this path. And it will return an edge, like the value of an edge that have like a smallest value along this path. Right. So the trivial way you can do is just look through, like read through this path, right? But dynamic tree or top tree allow you to do this thing in log n time. Or you can query for the minimum value in like a minimum value of an edge inside the tree. Let's say I query here X and look at everything in the subtree and return minimum value inside a subtree. You can do it too. Yeah, so everything takes log n time. So it turns out. So that's very good in theory. Yeah. But by the way, like it seems that in practice that they never use it because they say it's always slower to use it. But it really great in theory. So by the way, like because of this, it made me ask the following question, like because it seems that anything that is dynamic on trees are just easy because of dynamic tree data structure or top tree. So is there any problem that is easy in the static setting on trees, but hard in the dynamic setting? I don't know about this. It would be interesting to show some conditional lower bound or something like that. But the point is that, yeah, like all of this kind of update or query operation, you don't need to be worried about. Can do it fast in theory. Okay, now let's see what we will do, how to use this dynamic tree. So the invariant that I will we will try to use dynamic tree in this push relabel algorithm, right? And you should imagine that initially, like every node is at level 0, right? And you should think of the case where like initially every node is its own tree. Like it's just a rooted tree that have just one node. That is how it is look like initially. The T of U is U initially. But the invariant that we wanna maintain is this. So each node can have like one edge, one tree edge to only one node to the next level, to the lower level. So think of this as a parent. Okay, each node can have one parent. So if you look at if this is the case, then basically each node may have one parent. Some node might not have a parent because it's a root. This node have one parent. So it will be basically really just form these three edges together, form a collection of rooted tree, right? Yeah. And what we will maintain, like given this collection of rooted tree, what we will try to maintain is that the active guy, the guy that have access on it, can be only the root. So if it is a root, then it can be active. This is what we want to do. Okay. And
I have a question here.
yeah.
So can the non-active vertex have parent in another tree as well, along with parent in like can it have parents in two trees?
No, because we really maintain the invariant that each node can have only one tree edge incident to it to the next level. So like, yeah. So a tree, like if you have U, there is just only one edge incident to you, one tree edge incident to you to the next level. And so there cannot be like any other tree edge incident to you to the next level. So that's why you are in a single tree. Yeah. Okay. And so this is like our collection of rooted tree that we want to maintain. Like we want to use dynamic tree on implement dynamic tree on this collection of tree. But the dynamic tree also allow you to have value on this tree edge, right? And the value that we want to put it into here basically would correspond to the residual capacity on that edge. We will try to maintain this, okay? But note that these values are not maintained explicitly, right? Because like when you add some, like dynamic tree allow you to like add some value along the whole path in very short time. So these values are not really maintained explicitly, but you can query the value and query the minimum value along some path and so on, but you don't have this thing explicitly. Okay. So by the way, because we want to maintain this, what does it mean? It means that when I suppose that I somehow say that I want to link this guy to this, when I said this is U and V and I want to link this, then I need to say that I change the value here to be this much, right? Like just to initialize the value of this edge on the tree, yeah, to be exactly this, so that this is maintained. Also, suppose that I somehow cut an edge. Whenever I cut a tree edge, it used to be here. If I cut it, then I need to kind of restore, like any edge here that is not a tree edge. Now I want to really explicitly set. Now I want to explicitly set set the flow value so that the residual capacity is value of E. And to do that, I just set it like this, right? Make sense? Or I mean, for any non-tree edge, we maintain the residual capacity explicitly. And for every tree edge, we maintain it implicitly. So these two things we assume that we always do whenever we cut and link, just so that we can maintain this. Okay. And now the algorithm is gonna be like simple too. So initially you start with empty flow and empty trivial labeling, and every node is a root of its own tree. The algorithm is here, like keep finding an active node, but now like the active node will be a tree root. Okay. So, and let's say that you get this guy, maybe this guy as an active node. And then you will just try to push or relabel just like in the same way. See if there is any admissible edge incident to this node. And if there is, then try to push in that direction. Maybe let's say this is U. Yeah. And suppose that this is an admissible edge. The residual capacity is of this edge, E, is more than 0. So this is admissible. So if this is the case, then we will try to push. I call it tree push because it do something a bit more than just push along this edge. Otherwise, if you don't have any admissible edge, then you relabel like before. So now tree push is like this. So first, you try to link link the tree. So you link this. Yeah. And what do you think we should do? Like, suppose that this thing has capacity. Like if the excess at u, let's say excess at u is 5, and this has capacity 10, but maybe this have capacity 3. What should we do? We shouldn't just send flow from u to v, right? We should just send flow from u all the way to the root as much as possible as we can. Because we know before that when we try to do push, but if it is unsaturating, then there can be too many unsaturating push. So now we want to say that, okay, if this is the case, what about just push 3 all along this path? So this will be like count as a saturating push, right? Because this thing will be saturating after pushing all along this path. So this is exactly what we want to do. Like, imagine that you have u here, and maybe there is some tree here. So this you link, you first, if this is admissible edge, you link it here. And what you do is that you compute this thing, like compute, you look into this and compute the mean path from u to root of u. So this is now root of u, right? This is really just computing the mean capacity along this, mean residual capacity along this path. And take the minimum with the excess of u. Right? So you will basically try to send flow, psi many unit of flow from u to root of u. And how to do that? Just say that, just use change path, like minus, let's say that like the capacity is 10 and maybe this is 2, 3, 11. Then you say that you minus 2 on all of this, right? If the excess here is 5, then this guy is like the bottleneck guy, and you just say that you send flow of 2 units along this guy, and that will be, how to implement that? This is just the same thing as saying that everything here minus it with 2. Make sense? Yeah. Right.
Sorry, can I ask a stupid question? Like,
Yeah,
is it possible for like none of the edges will be saturated?
It is possible.
Like
But like when
or-
basically when you call a tree push, it is possible that you still don't get saturating push, but it only happened once. Basically later, like so think of it as that not too many such unsaturating push. I will try to bow it later soon.
Oh, yeah. Sure.
But most of the push, you see that it will be saturating. Yeah.
I see.
Yeah.
I see. Thanks. Yeah.
Yeah. So basically, like we have u and we have v, and we have like a root of u. So what we will do is just try to push flow, like, and there will be like, let's say this is like a minimum guy with capacity 2. We push this flow, and then this thing becomes saturated. So the residual capacity becomes 0. So what we would do is that we just scan through this path. Like using dynamic tree, we will be able to detect this edge that is saturated. And what we do is that we just cut it from the tree. Maybe there are more guy, not just one guy, then we cut it too. Yeah. And what we do next is that, okay, maybe after pushing this first time, there are still like some excess at U remains. So what we do we just like try to push flow from U to this guy. Like, so try to push flow from U to the root of U as long as you can. After pushing this to here again, maybe, okay, maybe this edge is saturated, so you delete. And then keep repeating until you don't have any excess left, or like or you don't have or like you become like, or you have saturated this edge incident to you already. Yeah. Like once you have saturated the edge UV, then you would cut this thing and U will become its own root. That's when you stop. Or so you stop when U become its own root, or the excess at U is 0. Okay. Is this step clear?
So there can be other edges from U that are still unsaturated, right?
Yeah, they can still be there, but this is a case when we try to send flow through from U to V only. Yeah,
one edge.
Yeah.
And then as this process, yeah, go ahead.
So yeah, we only keep cutting edges in this path basically, until we cannot do. That's the 3 push from U to V. Yeah, there might be like some admissible edge from U to other guy V2 V3, but that is like just we would do that when we like scan through the next admissible edge at U. Yeah.
And so we are cutting many times, so there are many trees that are getting formed. So all of those roots are active vertices now?
All of the root there might not be active, but only active guy can be the root.
Oh, is it? Okay, it's not a two-way thing.
Yeah.
Okay. Only active guy can be root. Okay.
Do you mean active must be root, but root is not necessarily active?
Right? I think so. 1 second.
All right. Yeah.
So yeah, root might not be active. Like for example, the first time that you send flow from U to the root here, this guy will be active after sending the flow, but this guy, once you cut this thing and this guy become a root, it might not have access on it. Yeah. So active guy must be a root, but the root might not be active. Okay. So that's 3 push. So it's really like try to push along the path as much as possible. Every time that we push, it will be saturating except the last time. Yeah. Okay. And next is like, when do we relabel? We relabel when you basically look at U and you don't have any admissible guy that you try to tree that you can try to tree push, then you will just relabel it, which is just to increase the level. But one thing is that when you try to relabel, you will actually cut like so now that you here might have like might have a lot of children, right? You here like you might have actually a lot of 3 children. What we will do is like we just cut this thing out and relabel you. This is so that like the 3 edge are only like we want to maintain the fact that the 3 edge only like can connect from U to V from the next level to yeah. We want to maintain this. Okay. So now let's analyze it. Why this is now fast. So there will be same implementation details. Well, like how to get an active vertex fast. That is the same. Just use Q to maintain active guy. And how to obtain admissible edge fast for each node. Use the same trick of having an order of a neighbor list and like so each node you maintain the current neighbor and scan through the neighbor. So with this trick again, we will charge the degree time to degree amount of time to each relabel. Okay. Okay. So now let's try to bound the total cost. And so note that when we send flow from U to the root of U in the while loop of 3 push, I call this operation push. Like basically 3 push have a lot of push, right? Every time that we implement this thing, I call this thing push. Three push have a lot of push, but and we can just define it in a similar way, like a saturating push and unsaturating push. A push is saturating if the psi is set is not psi is actually like not the excess of U. Psi is said to be this. It means that it will saturate some edge along this path from U to the root of U. Yeah, otherwise, we call it unsaturating push. And now we are ready to analyze the time. Why? Because let's look at the total time spent on relabel. This is gonna be the same analysis, right? The number of relabel is NH, but each of like by this charging argument, the total time of relabel is gonna be this much. Actually, why log n factor here? The log n factor just come from the fact that when you relabel, you might actually we do this thing too. So you might cut some 3 edges. How much time you spend? This is like a degree of U3 operation. And that takes degree of U log n time. So it's actually not just this thing, this amount of time that we charge to relabel of U. Actually now in this algorithm, the actual cost of relabel can be as much as this. So that's why the total time for relabel is this. Okay. And how about saturating push? Well, using the same argument, we can say that the number of saturating push is MH, right? You recall this. Yeah. And each push is just one tree operation. That is just to change, like to call change path with this value. This operation takes log n time. So that's why it's MH log n. So that's almost done, except that we need to bound unsaturating push. This used to be a bottleneck, but now comes the key observation. How many times the unsaturating push can be? This is at most number of links, right? Just look at this. Whenever you call tree push, you first link, and in this while loop, there can be only one unsaturating push. So number of unsaturating push is at most the number of link. Okay.
Unsaturating push is when psi is equal to excess of u, right?
Yeah.
That
Right.
can only happen once, and once that happened, it is empty, no
Yeah.
excess. Okay.
Right. Yes. So we have this thing. The number of links throughout the whole run of the algorithm will bound the number of unsaturating push. But the number of links is at most the number of cut plus n. So now it's been meant to bound the number of cuts. But how many times we cut? We will cut in two cases, right? So one sec. So when we cut only when there is an edge that is saturating. So the number of time, each time that we cut, we can charge it to the edge that becomes saturated. Or another time that we cut is when we relabel. Okay. So maybe this is not enough. I should say that this is the number of edges that become saturated. The number of times that an edge becomes saturated, or the number of edges that is scanned, like that is incident to you when you relabel you. But in the first case here, this is at most MH. Just using the same argument when we try to bound the number of saturating push. Right. And how about this thing? Well, like you relabel each node. When you relabel a node you might cut degree of U edges, and each node is relabeled H time. So this is at most MH2. So basically the number of cuts is O of MH. So which means that the number of unset push, the number of unset push is MH plus N, which is negligible. Yeah, so that's why the total cost for this is MH log N. So that finish it. Everything is bounded by MH log N. Right. So once you have this, then basically all the application we have seen is improve in theory. Okay, any question?
So could you explain why number of links is less than or equal to number of cuts plus n minus 1?
Oh, so basically, then like if you have that your collection of trees, like what you maintain is a collection of trees, and the total number of edges in this collection of trees is at most n plus 1, n minus 1, right? Because it's a tree. Yeah. So you can like you can add at like if you don't cut at all, do you agree that you can link at most n times? But now you have some cut, but for every time you cut, you can link again by. So that's why the number of link is more at most cut plus n. Right. So that's it. Okay, good. So yeah, next time it will be like local version of push relabel and dynamic version of push relabel. Yeah. All right. So thanks. Yeah, I will upload this soon. Yeah. See you. Bye bye.
Thank you.